Good day, everyone. We are from Section 1 from SATK 3323, and today we'll talk about all things distillation. And here is our group member.
Have you ever wondered how we can get petrol for our cars from thick and black crude oil? The answer is via distillation in the refinery. So, what is distillation? Distillation is a separation technique whereby liquid mixtures are separated by their boiling point. The first type of distillation is simple distillation. The diagram shows setup of a simple distillation during laboratory. The mixture is heated in a flask, and the component with a lower boiling point will evaporate first. This process is best for separating a liquid from a solid, for example, making a pure water from seawater. The second type of distillation is flash distillation. This is a continuous process often used in industry. When we suddenly drop the pressure of a hot liquid, it will instantly turn into vapor. The diagram on the right is an industry setup. Here we use a heat exchanger to warm up wastewater. After separated into distillate, the clean effluent is removed from the bottom. The third type of distillation is differential distillation. As the liquid mixture is heated, the more volatile component will leave first. The liquid remaining will become richer in the less volatile component. What does MVC and LVC mean? MVC stands for more volatile component. It has a lower boiling point and prefers to stay as a vapor. While LVC stands for less volatile component, it has a higher boiling point and prefers to stay as liquid. This diagram shows us the composition of a vapor and liquid at a specific temperature. YA represents the mole fraction of component A in vapor phase, while XA is the mole fraction of A in liquid phase. Raoult's law allows us to predict the composition of component in vapor or liquid. This is the formula of Raoult's law. Lowercase pa represents partial pressure, while uppercase Pa is the vapor pressure of pure liquid multiplied by mole fraction of A.
Moving on to VLE diagram. So what is VLE diagram? VLE stands for vapor-liquid equilibrium. So VLE diagram is a diagram that shows the relationship between the mole fractions of the liquid and vapor phases in a mixture. Before looking into VLE diagram, it's very important for you to understand bubble point and dew point. Bubble point is the first point at which the gas is formed when a liquid is heated, while dew point is the first point where the liquid is formed when the gas is cooled. There are two types of VLE diagram. One is TXY and another is PXY. In TXY diagram, we are focusing on the relationship between the temperature and the mole fraction. But for PXY diagram, we are focusing on the relationship between the pressure and the mole fraction. Let's say we have two compounds A and B, and we combine them together to become a mixture. So what are their mole fractions respectively? Mole fraction of A can be calculated by number of mole of A divided by the total number of mole, so we get 0.6, and the mole fraction of B, we can calculate it by 1 minus mole fraction of A, so we get 0.4. So from here we know that the summation of the mole fraction of A and mole fraction of B must be equal to 1. But when the mole fraction of A is 0 and the mole fraction of B is 1, this indicates that it is a pure substance, which is pure B. And when the mole fraction of A is 1 and there's no B inside, which means the mole fraction of B is 0, this indicates that it's actually pure A. Let's say A is more volatile than B. So which TXY diagram do you think is correct? Remember, A is more volatile than B. The answer is the left TXY diagram is correct. Why? So this is actually because A is more volatile, so it has a lower boiling point than B under constant pressure. By comparing TXY and PXY diagram, we notice that the shapes are mirrored. You'll notice that in PXY diagram, the right side, which is the pure A side, is higher than the left side. This is because A is more volatile, so its vapor needs higher pressure than B to turn into liquid under constant temperature.
Well, thank you, my friend, for the well explanation of the above topic. Now, I'm going to explain the TXY diagram in detail. So I pick TXY diagram for the benzene and toluene system at 1 atm. So let's say the feed is 0.4 of mole fraction. And then below the blue line here is the cold liquid, which means that the benzene exists as liquid. Next, uh, at the blue line here is a saturated liquid. It means that the first bubble point will appear. Next, at the middle, at the between the orange line and blue line here, it will exist at a vapor liquid mixture between the benzene and toluene system. And then at the purple line here, it will exist as saturated vapor, which means that the dew point is exit. Then above the orange line here, the vapor, the benzene will exist as a superheated vapor. Next, I'm going to teach you guys what if the feed is given and what is the temperature needed for the distillation column to function. So let's say I choose 0.5 mole fraction of benzene entering the distillation column. Then we need to draw a straight line. After that, is touch the curved blue line here, and the touching point here, we will draw a horizontal line. Then between the curved orange line here, and then we will draw straight down. And then after that point is, let's say, and we get 0.73. What is mean that? This means that the mole fraction of benzene at the top of the column here is 0.73 in vapor form. And then next, we'll draw another straight line, and then the temperature here is 363 K, which means that the distillation column needed 363 K of temperature to achieve this separation. Next, what if the temperature is given? Let's say I choose 370 K, and then we will draw a straight line, first touching the blue line here, and we'll draw straight down, and we'll get x equal to 0.3. And then continue drawing another straight line touching the orange line, and then we'll draw down, and we will get y equals to 0.54, which this means that at 370 K, the distillation column feed needed 0.3 feet of mole fraction of benzene in order to achieve 0.54 of the at the top of the benzene column.
There are two main applications of distillation. First is crude oil refinery. You may wonder, what is crude oil? Crude oil is a multi-component mixture where each hydrocarbon chain has a different boiling point based on its molecular weight. Distillation separates it into different products based on their thermodynamic properties. Second is water purification. This method is commonly used in school laboratory to produce pure water by heating impure liquid to become steam and then cooling it down to distilled water. Now let's further elaborate about crude oil refinery. So it uses continuous fractional distillation method to separate components in the crude oil based on their boiling points. This helps scientists convert raw crude oil into high-demand fuels such as gasoline and diesel used in vehicles and liquefied petroleum gas used in kitchen. The diagram on the right shows clearly what each component can be used for at different temperature range. Now moving on to the application of water purification using distillation. Multi-stage flash MSF is one of the most important or useful application of water purification at large scale. It involves the heating of seawater. Usually, heat from a nearby power plant is used to save energy. Then the seawater will be instantly boiled, or in other words, flashed into steam due to the sudden decrease in pressure. Then, this pure steam is cooled down to turn back into fresh water. Picture on the left shows the largest MSF desalination plant located in Saudi Arabia. Here is a summary page from subtopic 1 to 4. It includes all the information needed as well as important equations that you may refer and use in your studies.
Here is the reference that we used to produce our video. Thank you.